Okay, can people hear me and see my slides?
Yeah, we can hear you.
Okay, great. Thank you. So I and the talk presentation is 40 minutes. Okay. So let's start. So okay, so I like to situate whenever I talk about robots and autonomy, I always like to situate in the context of biology and evolution. And the main points are that intelligence arose when animals started to move. And so the key benefit they got was they could go find food in different places. So for this, they needed a locomotion capability. They needed perception, and perception helped in navigation, guidance to where do we go. And then something like 5 million years ago, you have the emergence of humans from primates. And this is when you have the hand becomes available because we are bipedal. So we are walking on 2 feet.
We already maximize for one.
Can people see the screen? Is it okay? Okay.
Yeah, we are okay, but because the sound is a little bit slow, we're trying to solve this in 1 minute.
And make sure he's speaking close to his microphone.
Yeah, Professor, could you
Okay.
speak closer
I
to
will
your
try
microphone?
to do that.
Yeah, we're good now.
Okay. Okay, so then 5 million years ago, you have the emergence of bipedalism and humans with hands, and therefore the development of tool use and a variety of dexterous manipulation skills. And then about 100,000 years or 200,000 years, we have the emergence of language. So language is important, but most of the history of evolution is where intelligence is really the connection of perception to action. So if we go to present day robotics, I think of there being three central problems. And the three central problems are locomotion, navigation, and manipulation. And let's look at where progress is in each of these fields. And I apologize that the examples I'll use will be biased examples. They'll be based on my group's work at some at Berkeley, some at Meta. So let's start with locomotion. So I'll start with this result, which is from our paper we presented at NeurIPS a few months ago. And this is on humanoid locomotion. And essentially, what this tries to show is that humanoid locomotion is close to a solved problem now. Now, walking on this kind of flat ground, you might think as relatively easy, but we can also walk on these kinds of terrains. So these are hiking trails near Berkeley. And the robot has walked for hours in this kind of setting. And it's really quite robust. Okay, so locomotion, that was locomotion. Now let's talk about navigation. So what is the navigation problem? So I'll talk about this paper which we presented last year at RSS. So the problem of navigation is go to any object or location of interest. So we did this experiment by going to various Airbnbs. So I wanted a really robust experiment. So our experiment was you go rent an Airbnb, you open the door, you put down the robot, and then the robot's task, you specify a task. So the task could be go to a flower pot, go to a TV, go to the kitchen, whatever. And it has to do that, and you can measure success in that setting. So that was our setup, and let's see how well we can do. And there's no prior knowledge of the map or any such thing of the environment. You have to build up a map. You can build up a map if you like, but it has to be as you go. So let's see how it works. So this is the setup. We have this. So you can do this on any embodiment. Here we've used the Spot robot. It could be a wheelbase. I mean, that doesn't matter. The observation is shown in the top left. So this is like it's the picture that it sees. And it's been given a goal. So the goal window here, goal is specified here by an image. It can also be specified by language. And in this case, the goal looks like finding the kitchen sink. So what the robot is going to do is it's going to keep collecting observations. It's going to keep building a partial map plus semantics. And then as it moves, it at some point it finds the goal, then it declares success. So, and then we give it the next goal. So let's see what happens. So this is the map being built. So the map is growing on the top bottom left. The robot is right now just wandering around. It's not got to the kitchen sink yet. I mean, see, a lot of this is sort of fruitless, but once it got to the kitchen, it saw the kitchen sink, success. Then we gave it a new goal, red cup on the brown leather chair. Okay, and okay, it found it. Okay, then you gave it a new goal. This was like a sofa. Now, as you see how as it moves, it's sort of building a list of the objects that it sees, and then the map is growing on the bottom left. So this is the key idea. So this way you get efficiency in the sense that you don't, if there's an object you already seen before, you don't have to, you can just go there. You don't have to do a blind search anymore. And here are the kinds of objects, and then I mean, here the map is being built up and the semantics are being built up in real time. Okay, and then we tested it quite seriously, right? We have all these different kinds of objects, and you can specify them by an image, by a language, and basically it works. So now let's look at manipulation. So in manipulation, manipulation is where a lot of the action is right now. Right now, most of the interest is in manipulation, and particularly, I believe it's in dexterous manipulation or bimanual dexterous manipulation. So let me show you some work which is from our side, and this is using a paradigm which has now become very common, which is that you convert this problem to a supervised learning problem. So you collect trajectories of humans teleoperating a robot to do the task, and then you collect maybe 1,000 such trajectories of the robot picking up a banana, and then you use that to now you train a policy, and then of course you just run it. So here we are using the embodiment that I favor, which is multi-fingered hands. A lot of the work nowadays is done with parallel jaw grippers. And I don't like that because I don't believe that the future is in parallel jaw grippers, at least if you want truly general mechanical intelligence in the home, for example. I mean, you will need to have multi-fingered hands with tactile sensing. So let's see what we can do though. So this is a variety of tasks. And by the way, the wine pouring task, if you tried to do it with parallel jaw grippers, I don't think it would work very well. It would certainly not work very robustly. Okay. So now, so this is an example, and I mean, of course, I mean, you can watch lots of videos now of various companies who have results in this area. So let's look at do a status report where we are. Locomotion, good progress. I mean, in fact, locomotion connects to whole body control, which is not fully solved yet, but I think we have made good progress. Navigation, I think of as nearly done. Manipulation is a long, long way to go. We are very far from human level competence. We are not going to get there in 1 year, 2 years. Okay. And if you think of the leading paradigms where we have had success with machine learning techniques which use data. The data for language and vision was readily available on the web. The data for robotics is not readily available on the web. And also our techniques are inefficient. Our techniques for learning, for example, large language models, they are quite inefficient compared to humans. So rough number is think of how much data a child needs to learn language and how much data machine needs. So LLMs will operate from like say 1 trillion tokens, 1 trillion words. And human babies by the age of 10 have heard maybe 100 million words because the estimates like they hear a million words a month. So by the age of 10 years, it's about 100 million. 100 million, 1 trillion. So that's a factor of 10,000, 10 to the power 4. Okay. And we expect similar behavior in robotics, and this is going to make learning brute force hard. So one thing I believe in philosophically is that we need to have more efficient ways of learning and more clever ways of learning, and we can get a lot of inspiration from child development. And here is my favorite quote, which actually goes back to Alan Turing 75 years ago, who wrote that instead of trying to produce a program to simulate the adult mind, why not rather try to produce one which simulates the child's? If this were then subjected to an appropriate course of education, one would obtain the adult brain. And Turing had this insight 75 years ago, and people have operationalized it by saying, okay, learning is the answer. But there is more than that. There are the details of how learning, what kind of learning, how to stage it, what is the curriculum, what's the reward. I mean, all of this is part of our research enterprise. And now we know a lot from child development. So our colleagues in psychology have done a lot of work, and this is sort of a paper from Smith and Gasser, which has a lot of insights. And these insights are about child development, but I think they can directly inspire and help AI. So let me convert some of these insights into specific statements, which I will then subsequently show you some examples of in our research agenda. So for example, multimodal means don't just use one sense, don't just use vision. Normally people when they say multimodal, they mean vision and audition, but in the context of robotics, vision, touch, and proprioception. Incremental means that you need to have hierarchical systems with control and planning. Embodiment matters. Search is fine. Imitation learning, you learn from others. And then there's a role for language, particularly with respect to higher level plans and common sense knowledge of a certain type. So then I want to take people who come from a computer vision background to emphasize what are, I think, novel, interesting things that we have to worry about in the robotic setting. And at least this was insight to me when I moved from computer vision to robotics. So in computer vision, one of our big realizations was something like around 2000 that we cannot do recognition by focusing just on single instances. We needed to do generalization over the different instances of a category, pose, lighting, etc., etc. And how we do that, we made that a supervised learning problem. In motor control tasks, you have a feedback loop and you have to deal with like a robot walking in different conditions and so on. So what is needed is, one is the idea which comes from control theory, robustness to disturbances. You have some disturbance, you have to eliminate that by using feedback. And the other is adaptation. And this term has also been around in the control literature, adaptive control. So your robot has to walk in different kinds of physical conditions. So these ideas, these are the big concepts. And whenever we evaluate some work in an autonomous system, we should look for these three criteria. Do you have generalization? Do you have robustness? Do you have adaptation? And I'll give you an example from a line of work from our group, and this is like from 4 years ago, basically. And this is we call this rapid motor adaptation, but I'm using this as an example because it illustrates the issues quite well. So in this case, what we were doing was training a policy for a quadruped to walk. Okay, and this quadruped has to walk. It could be in sand, it could be in hard ground, it could be up slope, down slope, etc. And that's what we are going to train with RL and train some policy. But you need it to be adaptive. You need it to work in different conditions. So that is captured by this variable Z. So Z is some latent which captures aspects of the environment. And this has to be estimated online. And it turns out that the idea is that we can estimate it from the past history. And you try to use perception, but you use past history. So the sequence of states and the sequence of actions from the past, those feed into this neural network called the adaptation module, which enables us to estimate Z. And this whole thing these can all be trained in simulation. So let's give an example here. This is of a robot trying to walk on this mattress, and this mattress is slippery because there's some oil that has been poured on it, and it's going to struggle initially, and then it's going to recover. So it's struggling, and then it recovers. And the way it recovers is because of this estimation of the Z, which the lower two curves show that that initially there is some estimate of the terrain basically, and then that estimate is wrong, and then as it corrects itself based on the past history, it can recover. And this enabled us, and this is like 4 or 5 years ago, to get results like this, which at that time were very noteworthy, that we could walk with exactly the same policy, trained completely in simulation in a very wide variety of conditions. And this is why this idea of rapid motor adaptation took off. But here is a more later development of this sort of thinking, and this is in the context of humanoid locomotion and and there we had these two stages, which was this adaptation module and then the actual runtime system, the neural network for the policy. And here the idea was, can we do it just with a bigger model? And it was a transformer model which has more context, and then it can learn. And you can see examples of that here. Right? So you notice how it walked differently and then it starts to walk again. So this is a blind robot. It doesn't know anything about the slope. It discovers that from the context of how its feet are reacting to its commands. And in fact, you can, if you probe inside the neural network, you can find neurons which correspond to these kinds of states and so forth. Okay, then so far these were blind robots. Why do we need perception? We need perception because it enables precise locomotion. And here's a paper from like a couple of years ago again. And here we took the idea, which was from the rapid motor adaptation work of being adaptive to the terrain. And now we added not just adaptation to physical parameters like friction and so on, but also to geometry. So the geometry of the terrain. And it turns out that you can do this adaptation without building a full SLAM type map. In fact, it may be a bad idea to try to build that for the local terrain. Okay, so so let's see how it. So this is this variable gamma here. The Z captures essentially the more like the physical parameters. And let's run this video. So here, this robot has a camera on top. It's an RGBD camera, and you're going to see on the top right what image it sees. And it's going to walk in a pretty difficult and challenging terrain. It's going to walk on these stools. And if it makes one footstep wrong, it's going to fall. And it has no prior knowledge of the environment. Everything it is going to build up is from what it sees. Anyway, I could go on, but you get the idea. And now, nowadays, you'll see many such videos. So quadruped locomotion, now there are many examples which show that this can be done robustly. But this work was one of the pioneering works which showed that this could actually be done. Okay. Next, so now I'm going to focus mostly on manipulation because this is where I think a lot of the challenging problems are. But I want to connect it up to these big ideas, which I think are all quite important, and I think that we need to we need to operationalize them and so on. So first is this idea of multimodality, and I'm going to focus on this in the context of manipulation. So the problem we're going to solve is in-hand rotation. So let me first show you a demo of the task. So this is the task. So what you see in different rows, this object is being rotated in the hand. What you see in different rows is rotation about different axes. X-axis in the first row, Y-axis in the second row, Z-axis in the third row. And notice generalization across many different kinds of objects, right? And then you need so adaptation to different objects, robustness, because when you are doing any motor task, there'll always be some disturbance and error, and you need to compensate for that. So how do we achieve this? So we achieve this using multimodality, multimodal sensing. So how we can solve various challenging action tasks is by making rich use of perception. So in this case, the perception comes from a camera. It's an RGBD camera which is looking at this object, and you'll use sort of standard computer vision tricks, segmentation, some kind of 2.5D depth recovery and so on. But also we have these fingers, and these fingers have tactile sensors, and these are the images seen by the tactile sensors. So these are going to give you a sense of the forces. When the object presses against the finger, there will be some normal force, some shear force, and we are going to get a sense of that. Okay, so you saw the task, and now the pipeline. So we call this a visual-tactile policy. So it's using vision and it's using touch, and it's got some processing going on. And overall, what's the architecture for training? Well, we have two stages as we did in the locomotion work. The top stage is training in simulation with privileged information. So you know, for example, the shape of the object, its pose, and its physics parameters, and those are encoded in this Z, and then you have the control policy. And at test time, you're not going to have this privileged information. What you are going to rely on are observations. So these observations come from vision and touch, and then they get fed into a visual-tactile transformer, which is doing the estimation of these latents, these Z's, and then of course you have a control policy on top, and that's what you saw in operation. Now our so one is to just show that we can do this, and what is interesting about this task is that it's very challenging and it's an agile task. So trying to do this with teleop would be quite hard. Humans will find it quite hard to do a teleoperation of this task because it's very agile. There are many steps that have to be taken in a certain unit of time. Now the question is this is a visual-tactile transformer. So did we get value out of the vision? Did we get value out of the tactile? And here's where we have these findings. So these show on the y-axis here is performance, and this is like how long you can keep rotating and so on. And the x-axis, these different bars correspond to different settings of what the input was. So this rightmost column, it corresponds to having complete ground truth information about the shape and pose of the object. So this is the oracle information. So your performance is best under that. The extreme left is when you only have proprioception, you only have joint angle information. That does give you some information because how the joints can move is constrained by the object. But then you have these two columns. One corresponds to just using vision, one corresponds to just using touch. And you get a decent performance with that. But if you use vision and touch, you get even better. So they give you complementary information. And you are almost as good as having oracle knowledge. So this slide is in a specific setting. I'm talking about one specific task of rotating an object in the hand about different axes. But I believe the lesson is general. The lesson is that you want to be using multiple modalities, and multiple sensory modalities will give you better performance. And I expect this will be replicated throughout. Now there is a question of how to do the touch sensing, and here uh, with cameras we don't worry about having to build a new camera. You just buy one, right? And the camera technology took many decades to develop. For example, like the basic technology for CMOS imaging and CCD and so forth was developed in the 1960s. But that led to digital cameras in the 1990s, and in the 2000s is when we got cell phones, and then really we had this explosion of billions and trillions of images on the web. Well, tactile sensing is much behind vision, but this sensor Digit 360, which is from a research group at Meta, is sort of the state of the art on how well you can do, and it has a lot of fancy sensors underneath, and it makes it kind of comparable to the human skin. In fact, it's better than human skin. I mean, underneath human skin, you have a lot of mechanoreceptors, which respond to force and or different spatial and temporal scale. So you can do things like if you hold an object in the hand, this water bottle, and it has got some liquid in it, and you shake it, from the different modalities, you can estimate whether the bottle is empty or half empty and so on. Okay, let me go on to give some examples of more motor tasks. So this is work which was presented last year at Coral, which is twisting lids off with two hands. So this is a slightly harder problem than just rotating an object. This is like opening a pill bottle or opening a water bottle, right? And we want generalization, so it should work across any bottle. And this is a bimanual task. So humans normally use one hand to hold the bottle and another one to untwist. And we use the same paradigm, learning in simulation, RL in simulation, and then applied to the real world, and note the generalization across different objects. So let's see it operating. So you see that the bottle's cap falls off. And what we find when we do this task is that really perception is key. So good vision capabilities for seeing this object are important. Okay, but now I've done two cases, right? Just rotating an object in the hand, now rotating an object, twisting a cap off with two hands. I mean, is this list, how long is this going to go on? How many of these do we have to consider? So if you think of the set of actions or tasks, it's really infinite. It's just like the number of sentences in English is infinite, right? But sentences are made up of words. So and number of words is not infinite. It's more like 30,000 or whatever. So this is a paper from about 2017. This is a computer vision paper called Atomic Visual Actions, and there's a data set called AVA, and you can look that up on the web. It was done with a team at Google. And what the starting point was this insight that while over a longer period you can have actions like, a basketball game or a birthday party or going through security at an airport, right? It's an infinite set. But if you look at what's happening at a 1 second time scale, it turns out that there is a much smaller set of possibilities. So there's possibilities which are around moving, like walking, jumping, running. But then there are actions which are around person-person interaction, and this is the large category, person-object interaction. And the idea is that you can compose these skills, this ability to do these actions for understanding bigger actions. So let's take this idea, which was for video understanding, and flip this around and use this for robots. So we call this common atomic manual actions. And here's a list of some of these. And let's actually look at examples. So these are all examples of insertion. Okay, but you can insert a Lego piece into another Lego piece. You can insert a USB into a USB port, a card into a card reader, etc., key into a hole. So generalization across objects, because language abstract. So insertion, these are all insertion tasks for language, but the details as a mechanical task vary. And we can give more examples. So there's examples of cutting. And then these are examples of actions without tools. So this is like a list. So so notice each of them has generalization embedded inside it for the different objects, and then we have a variety of these skills. And then more examples. And now my basic point is something like this. Consider a task like making an omelette. Well, I can break it down into atomic actions like you break an egg, you stir, you pour something into a pan, you flip things over. So those are atomic actions, and then there are a number of them that you kind of compose together. But if you have the ability, if your robot has the ability to do each one of these, well, then it might have the ability to do the full higher level task as well. And there we can draw on like large language models to figure out like what are the steps in making an omelette. But that low level capability has to be in the body of the robot. These skills can be trained with a variety of techniques. Reinforcement learning is what I used for those examples about rotation. It could be supervised learning with teleop. It could be visual imitation and any a combination of above. So let me show you some examples of imitation. And this is a paradigm which at Berkeley we've been pursuing for quite some time in the locomotion setting. I mean, these are papers from like many years ago. And to learn from humans, what needed to be done was to solve the problem of how to estimate the configuration and the pose of the body, all the joint angles of the body from raw video. And that took a lot of work. That's a computer vision problem. And Anju Kanazawa and I and various of our students have been doing it for the last like 7-8 years. And we feel that we have essentially solved the problem. I think at this point you can do this well and accurately, and it's good enough. Nothing is perfect, but it's good enough for training robot policies. So let's take an example in the locomotion setting. So here we have a transformer model. This was a paper at NeurIPS, and we will train from trajectories. And what's done here is training by a task of sensory motor prediction. It's like a sensory motor sequence where the tokens correspond to perception as well as action. And I won't get into the details. Some of these tokens could be missing, but that still enables you to train this kind of a model. And on a wide variety of data, for example, you have this data of people playing tennis, and now you can convert that to human body, from the human body to the robot body, and that's how we get this robot walking. And then on top of that, so this is a good way to learn good representations, good intermediate representations, because we have these high dimensional problems when you're trying to deal with humanoids or multi-fingered hands. And reinforcement learning is kind of finicky. It's because it's essentially in exponential search, so you want to be in a low dimensional space. So you can effectively get to a low dimensional space using this kind of learning from data. And once you have better representations, you can go back to reinforcement learning, which can train and go beyond the solutions that you just observed. And here are some results. And these are on walking in challenging terrain. So challenging terrain here means steep hills of San Francisco. And these are the slopes. And then let's see some results. So it's pretty hard, but we can do better. So this is in fact the steepest hill in San Francisco. So there's a segment here which is at 41 degrees slope. So will it be able to do it? So so and then you get robustness, which is the usual way people test robustness. And then I'll show you some more recent results from other members of our Berkeley group, which is video mimic. And this is here, what was done is that we did video analysis, which showed recovered not just the pose of the robot, but also sorry, pose of the human, and also the 3D environment. And again, the technology is getting good for that. So let's see how what that enables. So this is the training data, humans doing these tasks and just recording it with video. Anyway, these ideas apply not just for locomotion. I mean, I've shown you examples with locomotion, but also for manipulation. And here, it's a more challenging problem just because the computer vision part of it is harder, which is reconstruct these. So suppose you have videos of like 100 days of hands, and you have humans manipulating objects. You want to recover the hand in 3D and the object in 3D. And if you have that, you have trajectories you can put into the simulator. And we've been trying to do this for some years. This is a paper from ICCV 2021, and we have some more recent results on it. And this is work led by Jane Wu, and building on much better technology now for reconstructing hands, something called Hammer, and then uh, uh, techniques which enable us to get to the model of the 3D model of the object. So these are reconstructed. So you have the hand and the object in 3D. So anyway, you see how the reconstructions are. So I think this is essentially on the threshold of big success, because uh, I mean, this technology is getting really quite good now. I mean, it could get better still, but at some point, basically, this could be the replacement for learning from teleop, because collecting teleop trajectories is very hard and painful, and particularly becomes extra hard when you try to do dexterous with multi-fingered hands. And now with video, all this data is free. So potentially we might use this for doing the basic training and use the teleop trajectories for just fine tuning at the end. So yeah, more examples. And this is my concluding slide. And contrary to where a lot of the robotics community is, which is a lot of the discussion is about these big VLAs and how to solve the high level parts of the problem of how we bring in common sense knowledge of what are the steps in making an omelette. I feel that it is ultimately going to flounder if you cannot do the low level skills. And these are the skills which a child learns between the age of 0 to 5. They learn how to walk. That's a robot skill. You cannot learn to walk by just reading about it. To learn to walk, you have to walk in the body of the robot. I cannot become a good tennis player by just reading about how tennis is played. Okay, you need skill in your body, in your embodiment, and this is a variety of skills, but a relatively small number of atomic skills. If a robot has that capability, those can be composed together to achieve tasks, and that part does require that kind of common sense linguistic knowledge which is present in LLMs. So this is my general thesis. So I feel that we are in an exciting time for robotics and autonomous systems, but pay attention to the low-level parts of the problem is the moral that I want to communicate. Thank you very much for your attention.
Thank you very much, Malik, for excellent talk. Any question from the audience? You can please go ahead and use the microphone to ask questions. Yeah.